Hi everyone, and welcome to Infinite Sets with me. Today we will be determining whether or not we can count the number of elements that is in an infinite set. So what I mean by that, if I said that the natural numbers have infinitely many elements, then hopefully you're going to agree. The number of integers is also infinitely, there are infinitely many of those. The number of real numbers, infinitely many of those. So the question is, are these all the same infinity? No. We're going to talk about two different types of infinite sets today. The first type is countably infinite. And we say that a set A will be countably infinite if it is equivalent to the natural numbers. And that's because natural numbers, infinitely many of them, but we can start at 1 and go through a nice counting progression of 1, 2, 3, all the way up to infinity. And so that would be countably infinite. Otherwise, we're sitting in the land of uncountable. So if it's not countable, then it's uncountable. There's too many for us to be counting. So the way our countability proofs are going to proceed are going to be fairly formulaic, because we need to be able to get this equivalence with the natural numbers. How do we prove that two sets are equivalent? With a bijection. So here's our template. Step 1, we need to define a function. We can do it either from A to the natural numbers or from the natural numbers to A. Really, it depends on the problem, which one's going to be easier. I feel like this one's usually easier. I feel like that one is usually how it goes. And then step 2, it can't just be any old function. It has to be a bijective function. So we're going to prove f is a bijection. Because once we have it's a bijection, that means you can say that a is equivalent to the natural numbers, which means that a is countably infinite, as per our definition that we've just gotten. Okay, let's take this for a run. Let's look at our first example. First thing that we're going to prove is that the set Z is countably infinite. And I remember the first time I saw this, it broke my brain. I was just like, oh, but natural numbers are a subset of Z. Like, how do you want me to make a bijection between these? What are you talking about? This is insanity. It's okay. We can do it. They are the same type of infinity, and that's what we're about to prove, even if it may feel a little uncomfortable at first, but it's okay. So what do we have to do? As per our template, we know that we need to develop a function between the natural numbers and Z, and it's going to need to be 1-to-1 and onto. That way we can say that they are equivalent. So then the big question is, okay, well then, this is the hard part. What's our function? And we're going to use a fairly common trick right now. So here are our natural numbers, 1, 2, 3, 4, 5, 6. And the way we're going to do this is we're going to kind of alternate what we pick for these to map to. Like, I'm going to map the very first one to 0 because something's got to go to 0. Might as well make it the first one. And then what I'm going to do with 2 is he's going to go to 1. So nothing crazy so far. You're like, I don't understand how this pattern is going to be helpful. We're going to make 3 go to -1. And we're just going to keep switching back and forth between positives and negatives. So 4 is going to go to +2. But 5, he's going to go to -2. And then 6, that goes to +3. 7 would go to -3, blah, blah, blah. So this is the idea for our function. Hopefully you can see we're going to hit up all the integers this way. You can also see that we're not going to have any duplicates, like 4 and 5 don't map to the same place. You're not going to like have two natural numbers going to the same thing. Not a problem. Okay, but this is not an actual fully written function. So we gotta back up. So how do we write this formally? So proof. We're going to say we're going to define a function f from the natural numbers to z by, and then I don't know, f of n is going to equal, it's going to be some piecewise function. Let's take a closer look at how we're going to define this. Let's first look at the positives. So positive 1, positive 2, positive 3. The pattern here is we have 2 maps to 1, 4 maps to 2, 3 is mapping, or 6 is mapping to 3. So all the evens are what are going to be mapping us to the positive integers. And so then the function we can relate these guys through is, let's see, 2 is related by 1 by just divided in half. 4 is related to 2, divided in half, divided in half. So there's our first function. We're going to do n over 2 when n is even. And that'll get us all of the positive integers, which means we have all the odd integers now at our disposal for picking up the rest of the integers. So here's odds. Now we have to figure out how to relate these guys. So n is odd. Let's see. We can't simply, like, my initial instinct was just kind of like, I don't know, do that. So now it's going to pick up stuff going in that direction, but then it's like, oh, but like that means we're doing negative a half, negative 3 halves, and it's just like, oh, okay. Right, n is odd, so we can't divide it by 2. I can just offset it, though, by 1. So then the question is, do I want to offset it by a plus 1? Let's just give that a go. N is equal to 1, so then that would be negative 1 plus 1 over 2, which is going to be a negative 1. N is equal to 3, so that would be negative 3 plus 1 over 2, which would be negative 2. So that looks good, but that's not what we had written. We need that first one to map to 0. So what we want to do is we want to do a minus here. So minus 1. So that'll be a minus here. And that would map us to 0 and to negative 1. And that'll be good. Okay. So that's the hard part. Coming up with our bijection. Now we have to prove it's a bijection. And then once we have that, we're basically done. Let's make some room so that we can do a one-to-one proof. So this is going to start the same as any other one-to-one proof. We're going to take 2 elements in the natural numbers, since that's our domain. Let's use x and y. So let x and y be natural numbers such that their outputs are equal. There we go. First line of any one-to-one proof. Now what we need to do is prove that x is going to be equal to y, which is going to be kind of tricky because like 2 really different things are going to happen depending on if we're talking about even or odd numbers. So this is an excellent time to do proof by cases. Case 1. I'm not going to go through and do combinations of x and y and be like, x is even and y is even, x is even and y is odd. That's 4 cases. I don't want to do that. I don't have to do that. So case 1, just looking at x is even, and then case 2 would be just what happens if x is odd. I can use that x is even to my advantage. I can figure out something about y. That way I don't have to go through and do every combination of y with x. So how do I do this? So if I've got x is even, I know something. I know something about the output f of x. Then f of x, then f of x is going to be equal to x over 2 And since x is positive, right? X is a natural number, so x is positive. That means f of x will also be positive. Now, f of x is equal to f of y. So then we can say f of y is also positive. Now, the only choice for output is going to be that form, because if it were negative, it would look like this. So since it's positive, we know that it's going to be of this form, so we can say that then f of x, or f of y, is going to be equal to y over 2. So here we go. Now we know what f of x is equal to. We know what f of y is equal to. And we also know that f of x is equal to f of y. So since they're equal, that means we can say that they're outputs. So x over 2 and y over 2, we can say that that is equal. And then I can say, with a little bit of algebra, x is equal to y. And we are halfway there. So case 2. X is odd. So that means that f of x is equal to negative x minus 1 over 2. And that's going to be less than or equal to 0, right? 0, negative 1, negative 2. And now again, we're going to use the fact that f of x is equal to f of y. So f of y is also less than or equal to 0. That means his output is of this form, because that's the only way we're going to end up with less than or equal to 0. The other one was positive. Okay. So then we'll write the same thing, since f of x is equal to f of y. How do we know that? Again, because that was the first line of our one-to-one proof. So we're going to get x minus 1 over 2, negative y minus 1 over 2 are going to be equal, do some algebra in there, fill in the blanks. X equals y. We get to say that f is going to be 1 to 1. There we go. Okay. Now we've got to do onto. So now we're going to start with how every onto proof is going to start. We pick an element and we put it in our codomain. And now the goal is to show that we can indeed find a way to map to him using f. But again, depending on if b is like a positive or negative or 0, gonna be very different things that are happening. So let's split it up. Right, this is the part that's going to be positive, and then this part is less than or equal to 0. Let's use it to our advantage. Case 1. B is a positive number. So that means B is going to be a positive integer, right? Because he lives here. I need to find a way to map to him. Let's see. So I had f of x equals x over 2 when x is even. I'm going to use that to my advantage right now. What I want to do is I want a number to plug in so that when this happens, we get it's equal to b. That way I have found the element that is going to let us map to b. So kind of working backwards, 2b seems like a great candidate. 2b. So then now we have to write this up formally. I'm kind of scrambling around trying to figure out how to do this. now let's actually go for it. So I'm going to say let A equal to B. That means that A is positive, or I don't have to write that out. So A is positive, and it is even. So if A is a positive and even number, so then there exists A equal to 2B. Since it is positive, that means it's a positive integer, that means it's a natural number, such that f of A is going to be equal to f of, or is equal to A over 2, because, again, A is a positive even. So that is going to be, we decided A was equal to 2B. There we go. So there we found it. So this is a great, that was kind of like a lot to chew. I would maybe even suggest hit pause now that you know where it's going. Hit pause, rewind. Watch that again, follow that logic. And if you really followed it, you should be able to do case 2. Go and try case 2 by yourself. Okay. So then hopefully this is a few minutes later for you and a few seconds for me. Case 2 is B is less than or equal to 0. So now I have to find the right input again. So then the question is, I want some number A to be equal to B. So I'm kind of like doing my logic a little bit differently this time, hopefully in hopes that if it didn't work the first time, this will maybe gel better with you. So if f of A is equal to, sorry if that was noisy. If f of A is equal to B, that means I'm looking for a number A so that when I plug it in, like, I'm going to get this is equal to B. So all I have to do is I have to rearrange this equation and solve for A. So A minus 1 over 2 equals negative B. A minus 1 equals negative 2B. A equals negative 2B plus 1. Okay. So then I'm going to say let A equal negative 2B plus 1. So then if we start plugging in negative numbers or 0, like if we plug in 0, then we're left with 0 plus 1. If we plug in any negative number, that means it's going to cancel out with that negative right there. And so we're going to have, so B is less than 0 implies that negative 2B plus 1 is really equal to a positive number plus 1. And so we're going to get 1 and things bigger than 1. So again, A is safely a natural number. Okay. So let A be this particular natural number. Indeed, we can rewrite it. Then A is going to be equal to 2 negative B plus 1, where B is, or negative B is going to be a integer, right? So that means that A is odd. So that means we're in the land of plugging in now this piecewise function, right? We have A is odd. So then there exists A, specifically equal to negative 2B plus 1. That is a natural number such that f of A is equal to negative a minus 1 over 2. Is that the function? I have to check myself. Yeah. Okay. Always double guessing. So then f of a is going to equal a minus 1 over 2, which is equal, and remember we get to do that because a was odd. And then let's go ahead, because I got rid of my scratch work. You can't see where that a came from anymore. So negative 2b minus 1, plus 1 minus 1, all over 2. And now you can show your some algebra here. There you go. So there exists an a. It is a natural number such that f of a is going to be equal to b, which means that b got mapped to from the domain. And then we did that game in both cases. So no matter if b is positive, if b is 0, if b is negative, we're good. We're gonna map to it. We found the right candidates. Okay. So that means we now get to say that f is onto. Okay. And I'm going to make this, now we have our template ending for accountability proofs. Step 2 is very long if you can't see it. Step 1 is hard, and then step 2 is tedious in that template. So since f is onto, that means I can say, so f is a bijection. That means I know that the natural numbers are equivalent to the integers, and then by definition of countably infinite, the integers are countably infinite. And we are all done. Okay. So that's proving something is countably infinite. Now what we're going to do is we're going to prove something is uncountable. The open interval 0 to 1 is uncountable. Now, hopefully you believe that there are infinitely many numbers in 0 to 1 in that interval, and there are more numbers in there than there are natural numbers, like more. And more in a way, not that z had more numbers than the natural numbers, because apparently it doesn't, because we can count them all. So let's look at this other type of infinity. In order to prove that this is not countable, so we want to prove this is true, we need to prove that there doesn't exist a bijection between these guys. Going through and listing every single function out there is impossible. We can't do that. And so how do we prove that we can't find one? Contradiction. You suppose that you can. So let's get started with a proof by contradiction. So by contradiction, we're going to suppose that 0 to 1 is countable. We're going to then conclude that since it is countable, then there exists f from the natural numbers to 0, 1, where f is a 1-to-1 onto function. So in order to finish this proof, I'm going to do something that is definitely, this is weird, and it's like a tool that you can put into your bag. I would not expect you to come up with this trick on your own. If math was left to me to discover, trust me, I would not have figured this out. Fun note, or fun fact. The interval 0 to 1 is all the decimal expansions. Of the form 0 dot like xxx. I don't like that. 0 dot stuff. So a bunch of digits, but the important part is we have 0 is the number before. So certainly anything that you plug in here, like 3, 3, 3 forever, that's going to end up here in this interval, for example. So now that hopefully you are convinced that everything in here is going to be of the form 0 dot digits, we're going to use that to our advantage. So since it is countable, we have this function, which means I can list this stuff out now. So that means f of 1 is going to be equal to 0 dot, and I'm going to say 1. The first digit is A11. Second digit is A12. Third digit is A13. And then I can do it again for f of 2. It is also going to have this format of 0 dot and some unknown digits. Then f of 3, 0 dot, a digit, another digit, another digit, digits that go forever. And you can do that down to like f of n, but really it goes on forever and ever and ever and ever. But since it's countably infinite, we can list them. That's what it means to be countably infinite. But what I'm going to do now is I'm going to take these numbers and I'm going to look at them and say, I'm going to build myself a new number by looking at those numbers. Let's see. So I'm going to define my new function or not my new function, my new number. And it is also going to be a decimal expansion of the form 0 dot some digits that we don't know. But I'm going to pick these digits carefully. I'm going to say that I want to look at all these numbers on the diagonal. And I'm going to say that it's going to be 0 if the diagonal number is not equal to 0. So that means that b of I is going to be different from this number, because if it isn't 0, I've made it 0. But if it is going to be 0, I'm going to say, fine, I'm going to change it to be a 1. So no matter which number you look at, it's going to differ by at least one digit, because across the diagonal, I have defined b to be, I've defined it to be different than everything that we've already listed. So then the problem with this is b is an element of 0 to 1 because it fits this 0 decimal digits business. So it's in there, but f has not mapped to it because it's different than everything that's been mapped to. But f did not map to it. So that means that f isn't onto, because it missed somebody. But that's a contradiction, because f is defined to be a bijection. So basically, what this boils down to is no such f can exist. Since no such f can exist, that means that 0, 1, that interval is not going to be equivalent to the natural numbers, which means that 0, 1 is going to be uncountable. So if 0 to 1 is uncountable, now what we can do is we can use that information going forward. And if you want to prove something is uncountable, if you can say that it's the same as this 0 to 1, like if it's equivalent develop a bijection between this guy, 0 to 1, and whatever set you think is uncountable, that's how we're going to prove everything is uncountable. So if you want to prove it's countable, develop a bijection for n. If you want to prove it's uncountable, develop a bijection for 0 to 1. Okay. So just to wrap everything up, I want to clarify that countable sets and infinite sets are different things. It's not even that countable is a subset of infinite, because countable sets could mean finite sets, right? We can count the number of elements in a finite set, but you could definitely have a infinite set that is countable, as demonstrated by our countably infinite definition. And then things that are outside of the world of countable sets, those are all going to be uncountable. So if you are talking about a set that is not countable, it has to be infinite. Can't have a finite set that's uncountable. That we can count that stuff. Okay, so with that, I will leave this here and talk to you next time.